Okay, this video is going to go over how to solve some problems with MATLAB. So what is MATLAB? Well, MATLAB is a very popular tool used by controls engineers and actually a lot of people in both academia and industry. Why is it popular? Well, because it has a lot of built-in functions that are useful for control engineers so they don't have to rewrite code all the time. It also has something called Simulink, which is a visual modeling software that uses block diagrams or something like them. And we'll get to that later in the class. So, how to model a linear system in MATLAB? Well, we can start with a system. We can, if it's linear only, we can get its transfer function. We can use TF, which is the transfer function in MATLAB, to form the system. And then we can simulate using different functions such as step, impulse, or LSIM. Now, if it's nonlinear, we can still do something. We can get the state space model. If it's linear, we can use the feature use SS, which stands for state space, to get the form of the system and essentially do the same thing that the transfer function did. Now, if it is linear or nonlinear, you could code your own solution like forward Euler, etc. Or you could use a function from the ODE solver. So for example, ODE 45 or the equivalent, you come up with a function that uses that. And these are only some of the simulation tools that you can use in MATLAB, depending on what your problem is. So let's go over one of the basic methods that kind of a lot of people go through when they start learning how to simulate systems, which is called the forward Euler method. So say we're trying to solve the following equation. The derivative of y with respect to time is equal to r, which is a function of time, times y, which is a function of time. So this is a time varying system. We don't have an input into it. It's first order. So the definition of a derivative in this case, well, dy over dt, which is the limit of delta t approaching 0. This is literally the definition of a derivative. That is the limit of y of t plus delta t minus y t over delta t. You can actually come up with an approximation for this, which is dy over dt. It's approximately equal to that delta t underneath the difference between the two time points. And now plug that into the equation there. So all we're doing is taking this solution for dy over dt, and approximating this guy right here. Now, we can solve for d of t plus delta t. That's just going to involve multiplying by delta t here, and then shifting this y over here. And essentially what you can do is say t index of k plus 1 is equal to y at t index of k plus r at t index of k times y t index of k times delta t. Or another short way to write it is y of k plus 1 is equal to y of k plus r of k, y of k, delta t. Now, that is the forward Euler method, and what's nice about it is that it works for linear and nonlinear systems. So for a linear system, if we have this state space model here for our dynamics, we can just say this part here is approximately equal to that approximation for our first order derivative, where we have k plus 1 and k. These two terms here are evaluated at k, and all we can do is shift stuff over to get x of k plus 1 is equal to x of k plus these same terms multiplied by delta t. Now we can group these two together, and that'll give us our discrete A matrix or discrete state matrix and our discrete B matrix, which is just delta t times v. Now for a nonlinear system, we can do the same thing. We would just have the same exact process to end up with x of k plus 1 is equal to x of k plus delta t times that nonlinear function evaluated at that time index. And note that you could actually use u of k plus 1 here or here instead of u of k if you wanted to. And that is useful for some cases. Now, the last thing I wanted to cover is MATLAB's ODE 45 function. So a higher order, more accurate method than forward Euler is the Runge-Kutta or RK4 method. But it's essentially the same idea. It works very similarly to the forward Euler method. Now, MATLAB's ODE 45 function uses something like RK4, but delta t is not fixed. The computer determines what this should be at different points. It's a variable step solver. And all I'm going to do for this is I'm going to provide a document with some MATLAB examples to go over different ways to solve things in MATLAB. So that'll be covered in that separate document. And that covers solving with MATLAB.